Students, we have discussed the buffer action in the case of acidic buffer. Now we will see the same for basic buffer and extend our discussion to the concept of what is known as pH of buffer solution. And the equation is correspondingly known as Henderson equation. Now we will see the buffer action for basic buffer. When I say basic buffer, children, we have already seen that your ammonium hydroxide, weak base with its corresponding salt, and therefore your ammonium hydroxide will be in equilibrium with its corresponding ions, ammonium ion and hydroxide ion, and ammonium chloride giving ammonium ion and chloride ion. Children, ammonium ion is a common ion, and therefore because of the existence of common ion, the backward reaction is favored and the forward reaction appear to be suppressed. Therefore, that is known as a common ion effect. Now, this system is called as a buffer mixture for a basic solution. Now, in this case of basic buffer, if we add OH minus, the addition of OH minus will not increase the concentration of free OH minus ion because it is hidden in the form of the corresponding weak base. Since we have excess common ion here, the added OH minus ion will combine with the existing ammonium ion to form the corresponding weak base. Hence, the weak base is formed whose dissociation is suppressed, and therefore the concentration of OH minus ion remains constant. When the concentration of OH minus ion remains constant, POH remains constant. What is POH? Negative logarithm of hydroxide ion concentration. That again remains constant. Therefore, children, when POH remains constant, automatically pH also remains constant. In the second case, when we add H+, we expect the combination of H+ with the existing OH minus ion to produce water, thereby decreasing the concentration of existing OH minus ion. But it does not happen because when the concentration of OH minus ion decreases, then the corresponding POH will increase. When the POH increases, then your pH will decrease. Children, but that does not happen. In this case of your addition of OH minus, the addition of H+, the added H+ will not combine with the existing OH minus, rather the added H+ will combine with ammonium hydroxide to form the corresponding common ion ammonium ion and water. Since the added H+ and the added OH minus, they are hidden, they do not affect the concentration of your free OH minus ions available in the solution. Since the concentration of free OH minus ion available in the solution does not change, POH is constant. When the POH remains constant, then automatically the pH is also constant. And that's about the action of your basic buffer, children. Your buffer is a mixture of weak acid and its corresponding salt, which resists the change in pH of the system upon the addition of a small quantity of dilute solution of an acid or a corresponding base. Now we will try to derive an expression for your pH of your acidic buffer solution or basic buffer solution. First we will try to understand the corresponding pH of acidic buffer solution, and then we will extend our discussion and correspondingly we can say the equation for your basic buffer solution, children. Now, pH of an acidic buffer. pH of an acidic buffer. Let me assume a weak acid HA equilibrium with corresponding H+ and A-, and the strong salt of HA, it is NaA, which will completely dissociate to form or ionize to form Na+ and A-. Children, let me assume I have taken 1 mole of HA or 10 moles of HA initially and 100 moles of your NaA initially. Out of this 10 mole, 1% gets dissociated. That is, the degree of dissociation is 1%. When we assume that very low degree of dissociation, alpha is said to be very, very low. So therefore, your 10 moles are taken initially and 1% gets dissociated. Dissociation of 1% means what? 10 into 1 by 100. That is 1 by 10, which is equal to 0.1 mole, children. Therefore, your out of 10 moles of HA, 0.1 mole of HA react. So when I say 10 mole of HA, 0.1 mole of HA react, remaining 9.9 mole of HA remains as such in undissociated form. And therefore here, after attaining the equilibrium, we have 9.9 moles of HA, we have 0.1 mole of H plus, we have 0.1 mole of A minus. But in this case, we have taken 100 moles of NaA, the corresponding sodium salt. Now all the 100 moles will react or will ionize to form your Na plus and A minus, and therefore 100 moles of Na plus and the corresponding 100 moles of A minus. Children, what is the concentration of your A minus in total? It is 100 plus 0.1, which is approximately equal to 100 itself. Because 100.1 and 100, they are nearly equal. 0.1 is much lesser when compared to what? Your 100. Therefore, the concentration of A minus in the solution, even though it is the sum of the concentration of A minus produced by the weak acid and the corresponding your strong salt, but the concentration of A minus given by strong salt alone is maximum. That is your 100. Therefore, in this context, concentration of A minus total will be equal to concentration of A minus given by your weak acid plus concentration of your A minus, concentration of A minus given by the corresponding strong salt. But this is approximately 0, children. It's much negligible when compared to what? That term. Therefore, concentration of A minus furnished by weak acid is much less than concentration of A minus given by strong salt. Therefore, the total concentration of A minus can be approximately equated to the concentration of A minus given by the strong salt itself. That is, what is the concentration of A minus, children? 100 moles given in a divided by the corresponding volume of the solution. But 100 moles is equal to 100 moles. That is the initial concentration of sodium salt what we have taken. And therefore, concentration of A minus in total can be taken to be concentration of salt itself. And that is equal to concentration of the salt taken. This argument is very important, children, for understanding the pH of our solution. Similarly, the concentration of HA, the initial concentration of HA is 10. And what about the concentration of HA during the equilibrium? It is 9.9. 9.9 is approximately equal to 10. And therefore, we commit to ourselves that the concentration of HA almost remains constant, and which is equal to the initial concentration of the acid itself, because it is very weak, and whose ionization is also suppressed by common ion effect. Since the ionization of your weak acid is suppressed by common ion effect, the concentration of weak acid taken initially is approximately equal to the concentration of the acid at equilibrium. And therefore, these two are primary conditions to understand the corresponding derivation of the pH of your acidic buffer. One of the conditions is, children, we have already illustrated here. The other condition is concentration of your acid initially is equal to concentration of acid at equilibrium, because the amount dissociated is very small. So that's about this idea. Now coming on to the derivation part of it, your pH. Children, when I say HA gives H plus A minus, we know that the dissociation constant Ka by law of mass action is equal to ratio of the product of the concentration of the products to that of the product of the concentration of the reactant. Here we have only one reactant, children, and that is your HA. Now, we want the value of your pH, and therefore eliminating or isolating the term H plus, we have it is A minus divided by active mass of HA, or Ka multiplied by active mass of HA divided by active mass of A minus will be equal to the corresponding H plus. Children, now we want negative logarithm of hydrogen ion concentration. We want negative logarithm of hydrogen ion concentration, that is called as pH. So take log on both sides. When I take log on both sides, considering this term as a single term, when we take log on both sides, log of Ka plus log of A into B will be equal to log A plus log B. Log of X into Y will be equal to log X plus log Y. And therefore, this term can be considered as X and this term can be considered as Y. Therefore, when we take logarithm, it is log of Ka plus logarithm of active mass of Ha divided by active mass of A minus will be equal to log of H plus. But we need negative logarithm of hydrogen ion concentration. So multiplied by minus 1. We have minus log of Ka minus log of Ha, active mass of Ha divided by active mass of A minus will be equal to minus log of hydrogen ion concentration. Children, negative logarithm of hydrogen ion concentration is called as your pH. Negative log of Ka is called as pKa. And therefore, minus log of Ka is called as pKa minus log of H plus is called as pH. Hence, the equation becomes pKa minus log of your acid divided by corresponding anion. Active mass of Ha divided by active mass of A minus will be equal to the corresponding pH. Children, now we have this minus, we can take inside the logarithm and say pKa plus logarithm of, it can be active mass of Ha by active mass of A minus, the whole inverse. This minus will go to the power as minus 1 and that is equal to pH. Hence children, pKa plus logarithm of A by B, the whole inverse will be equal to what? B by A. And therefore we have active mass of A minus divided by active mass of Ha. And that is equal to pH children. Now we have that is equal to implies pKa plus what is concentration of A minus? Concentration of A minus total is approximately equal to concentration of the strong salt. That is A minus given by the strong salt itself, because the concentration of A minus furnished by weak acid will be very, 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 very low. And hence, the total concentration of A minus is equal to the concentration of salt itself. And hence we can say it is logarithm of active mass of salt divided by corresponding active mass of acid. And that is equal to your pH. Children, therefore, pH is equal to pKa plus logarithm of salt by acid. And that is your expression for pH of the acidic buffer, which is known as Henderson equation. Now, similarly, we can derive for basic buffer children. We can put BOH here, B plus plus OH minus. And the common ion is B plus. Here BCl, we can say BCl, B plus plus Cl minus. And the common ion is your B plus. And the corresponding expression will be same, but for you replace, instead of Ha, we put BOH. Instead of A minus, we put B plus. Instead of H plus, we put OH minus. Instead of Ka, we put Kb. And finally we derive the expression as POH is equal to PKb plus log of salt by base. Similarly, for basic buffer, POH will be equal to PKb plus logarithm of concentration of salt divided by concentration of corresponding base. That is again Henderson equation children. Now, I hope you should have understood this concept of pH of acidic buffer, and we have extrapolated the same for your basic buffer. And that's about the pH of acidic buffer system children. Now we'll try to understand the next level of concept, what is known as hydrolysis of salt. Children, when I say hydrolysis of salt, a weak acid and its corresponding salt. For example, I would say your sodium acetate. Sodium acetate, when put in water, it will ionize to form acetate ion and Na plus ion. This acetate ion in aqueous medium, in dilute system, will get hydrolyzed. That is known as hydrolysis of corresponding salt. So hydrolysis, in the topic of hydrolysis of salt, we have got different cases, children. We are going to see hydrolysis of salt of weak acid strong base, strong acid weak base, and the corresponding weak acid weak base. Definitely salt of your strong acid strong base will not be hydrolyzed, because even if the reaction takes place, it will form the corresponding acid or base which is very strong. They will again further ionize. For example, let me say what is exactly hydrolysis of salt. I'll just illustrate once and then we'll go into the concept. Children, I have sodium acetate in aqueous solution will form, sodium acetate in aqueous solution will form acetate ion and Na plus ion. This acetate ion in excess diluted system, I would say very diluted system, it combines or water hydrolyzes this to form the corresponding weak acid and liberates OH minus. This is an equilibrium reaction, but very less, children. The reaction will take place because the hydrolysis is constant. The degree of hydrolysis will be very low. Now, during this reaction, you have the formation of weak acid. Now, in a similar manner, suppose if we assume that Na plus gets hydrolyzed by water, it should form NaOH and H plus. Now here acetic acid is a weak acid, therefore its dissociation again will be very weak because its partial dissociation takes place. Whereas sodium hydroxide is very strong, it will immediately dissociate to form Na plus and OH minus, and again these two combine to form what is known as their water. Hence, the salt of strong acid strong base, we will not discuss the corresponding hydrolysis because there is no point in discussing. The system will not be in equilibrium. The salt of any one of the components should be weak. Either acid should be weak part or base should be weak part, or both can be weak. Now we are going to discuss the concept of hydrolysis of salt of strong acid weak base, weak acid strong base, and both the components should be weak, that is weak acid weak base. That is what the point of interest now, children. Now we will see one by one. The topic of interest is hydrolysis of salts and its corresponding pH. We are going to see the corresponding pH of the solution containing your weak acid strong base or strong acid salt of weak acid strong base or strong acid weak base. First, we have three combination. The salt can be of weak acid and a corresponding strong base, children. That is sodium acetate. Weak acid strong base, that is sodium acetate. Children, I hope we will write somewhat lower here. Now, the three salts can be as your salt of weak acid strong base, that is sodium acetate, CH3COO minus Na plus. In this salt, the anion, this gets hydrolyzed, not the corresponding strong part. In the second case, we have strong acid weak base. Strong acid weak base, we have ammonium chloride. Ammonium chloride is salt of your ammonium hydroxide, which is weak base, and strong acid hydrochloric acid. In this, ammonium ion will get hydrolyzed. The third case is the salt of weak acid and weak base. Children, it is ammonium acetate. In this, both the ions will get hydrolyzed. Both your acetate ion as well as ammonium ion will get hydrolyzed. Now we will try to understand the corresponding reactions for the each hydrolysis, children. In the first case, acetate ion will combine with water and the system will be in equilibrium with its corresponding acetic acid with the formation of OH minus ion. Acetate ion gets hydrolyzed to form acetic acid and OH minus ion. In the second case, ammonium ion gets hydrolyzed to form its corresponding weak base ammonium hydroxide with the liberation of H plus. So therefore, this liberates OH minus, whereas the other one liberates H plus. In the case of the third one, acetate ion and ammonium ion in aqueous solution, they will be in equilibrium with its corresponding undissociated molecule, that is acetic acid and ammonium hydroxide. So that's about the corresponding three equilibrium reaction, children, for the hydrolysis of your combination of strong acid, weak acid, strong base, and the corresponding weak acid and weak base. Strong acid, strong base salt will not get hydrolyzed. Even if the reaction takes place, the products formed, which are called as your strong acid, strong base, they will further completely dissociate to form the ions, and therefore there is no question of getting established in the hydrolysis of your strong acid, salt of a strong acid and a strong base. So that's about the idea of your hydrolysis of salt, children. Now we'll try to derive the expression for pH for all the individual systems. We'll first identify that the pH for weak acid and strong base hydrolysis. Children, the first case is, I'll write the equilibrium reaction. CH3COO minus plus water will give you corresponding CH3COOH plus your OH minus. Now let me assume in this water we take an excess quantity, and therefore during the calculation let us not involve the concentration of water because it remains almost a constant. Now therefore let me assume that initially we have taken 1 mole of your salt. 1 mole of salt is taken initially, and let me say the degree of hydrolysis is your H mole. That is, out of your 1 mole, it may be 0.01 or 0.1 or 0.2 would have got hydrolyzed. And therefore, let me say H is called as degree of hydrolysis, and the number of moles reacted after T seconds is your H mole. Therefore, what is the number of moles remaining after T seconds? The number of moles remaining after T seconds or formed after T seconds will be 1 minus H in the case of your acetate ion. That is, remaining number of moles of acetate ion. Whereas in the case of acetic acid, your H moles of acetic acid will be formed and H moles of hydroxide ion will be formed. Therefore, children, the concentration of water, let us not bother. The number of moles of acetic acid formed is again H mole, and the number of moles of hydroxide ion formed is again H mole, because for 1 mole dissociation, we have the formation of 1 mole and 1 mole. Hence, for X mole, we have X mole of acetic acid and X mole of OH minus will be formed. Initially, we have taken 1 mole. Not all the 1 mole will be hydrolyzed. Out of it, some fraction will be hydrolyzed. Let that particular value be H, and that is your degree of hydrolysis. This H is nothing but degree of hydrolysis, and out of this, a fraction got reacted, and the remaining is 1 minus H. So, for H mole of acetate ion, we have the formation of corresponding H mole of acetic acid and H mole of your hydroxide ion. Children, let us assume that the total volume of the system is V, and when we say 1 mole is taken in a volume V, let the concentration be C will be equal to 1 by V. That is, concentration of system initially be 1 by V. Number of moles by volume of the system is called as your concentration. Therefore, the concentration of 1 mole of the substance is called as 1 by V, which is equal to C. For 1 mole, the concentration is C. For X mole, the concentration will be X into C. For Y moles, the concentration will be Y into C. For 1 minus H mole, the concentration will be 1 minus H into C. For H moles, the concentration is H into C. For H moles here, the concentration H into C. Do not bother about water because water is taken in excess. Children, now we understand the equilibrium constant as known as hydrolysis constant. That is your KH. Therefore, what is KH, children? KH is equal to ratio of the active mass of the corresponding products with that of the product of the active mass of the reactants. Here, water is constant. Let us not bother about that. We need to understand only the variable system, and therefore, your active mass of acetic acid multiplied by active mass of OH minus divided by active mass of acetate ion. So that is your first expression, children. Now, we will extrapolate the same thing and combine your KH with the corresponding dissociation constant of the acid. So we will try to understand the dissociation constant of the acid as CH3 COOH will be in equilibrium with corresponding ions CH3COO minus and H plus. Therefore, children, now what is your Ka for this? Ka is equal to active mass of acetate ion multiplied by active mass of H plus divided by active mass of acetic acid. Now, we have the expression for Ka, we have the expression for Ka, children. Now, when we multiply these two, KH into Ka, when we multiply on left hand side and right hand side, on the left hand side we have KH into Ka, on the right hand side we have the cancellation of your CH3COO minus concentration, because here it is in the denominator, here it is in the numerator. And corresponding acetic acid in the numerator, here acetic acid will be in the denominator. And only the two terms left on the right hand side will be active mass of OH minus multiplied by active mass of H plus. Therefore, the product of 1 into 2, 1 multiplied by 2 implies KH into Ka will be equal to active mass of H plus multiplied by active mass of OH minus, children. I hope you should have understood this, because I need not write the entire term and cancel and show for you, because we have acetic acid concentration in the numerator, we have acetic acid concentration in the denominator. The numerator and denominator will get cancelled. Similarly, your active mass of acetate ion is in the denominator, whereas here the active mass of acetate ion is in the numerator. Both will cancel, and the terms which do not cancel, the concentration terms which do not cancel are your OH minus ion in the numerator in the case of your first equation, and H plus ion in the numerator in the case of your second equation. Therefore, children, what is your H plus into OH minus? That is called ionic product of water. Hence, we have KH into Ka will be equal to Kw, because Kw is known as ionic product of water. That is your concentration of H plus multiplied by concentration of OH minus. Therefore, children, we have derived an expression between KH, Ka and Kw. Now, we shall understand KH in terms of the degree of hydrolysis. KH in terms of degree of hydrolysis, substituting this value, Hc, the concentration of acid, OH minus the concentration of your Hc, that is Hc, concentration of OH minus, divided by 1 minus Hc. Hence, 1 becomes, 1 implies KH is equal to H into C multiplied by H into C divided by 1 minus H into C. That is cancelling one of the C. We have KH is equal to H square C by 1 minus H. If your H is much less than 1, then 1 minus H is approximately equal to 1. Therefore, children, KH will be equal to H square C. KH will be equal to H square C. So, what is your H? Root of your H square C will be equal to Kc. H square C is equal to KH. The H square is Kc by C. H square is KH divided by C. And therefore, H is root of KH divided by C. Your hydrolysis, degree of hydrolysis is given by root of KH divided by C. And that's about the expression for your KH and H, children, including your concentration term C. Now we need to find the value of what is known as your pH of the system. The hydrolysis of salt, our aim is to find the pH of this particular hydrolysis system. How to find the pH? We need to know the concentration of your OH minus or H plus. The concentration of OH minus here, children. When we know the concentration of OH minus, we can find POH. From that, we can find pH, because pH plus POH will be equal to 14. Or we also know that Kw will be equal to H plus into OH minus. Therefore, what is the concentration of H plus? It is Kw by concentration of your OH minus. Now, from this equation also we can directly find the concentration of your H plus. Therefore, children, for want of space, I'll just rub off some of the information and proceed with the further derivation. That is, we need to know some of the basics idea. Here, the concentration of OH minus is H into C. The concentration of OH minus H into C, that's what we have written here. Now, we have Kw will be equal to active mass of H plus into active mass of OH minus. Therefore, active mass of H plus will be equal to Kw by active mass of OH minus. What is Kw, children? It is KH into Ka. So, we can say KH into Ka divided by what is active mass of OH minus? Active mass of OH minus is your H into C. That is what we have substituted. We have seen in the table. OH minus active mass is H into C. Now I can substitute here H into C. What is H, children? H is root of KH by C. Again I can substitute root of KH by C for your H. Now having done all these things, we can simplify this expression to understand the corresponding value. Now children, we can keep, instead of KH, we can keep directly in terms of KW itself, and hence we can derive KW by directly HC. Therefore, your derivation is H plus is equal to KW by what is the OH minus? Your HC. That is OH minus, children. Now, I can substitute instead of H, your root of KH by C, and then simplify your KH as your KH is equal to KW by KA from here. Therefore, that is equal to KW by, what is H, children? H is root of KH by C multiplied by C. Here, this can be split as root C into root C, and one of the root C gets cancelled. Therefore, we have KH divided by root of KH into C. That is, having done so much, just we need to do some more algebraic calculation to find the value of your corresponding H plus of the system. Children, that is equal to KW by root of KH multiplied by C. Because this is root C into root C, and one of the root C gets cancelled, and another root C can be clubbed with your KH. Now children, what is KH? KH is KW by KA. Therefore, I can substitute instead of KH, I can substitute KW by KA multiplied by C. Now that is your concentration of your H plus. Now bringing this Ka to numerator and writing this Kw as root Kw into root Kw, we have concentration of H plus will be equal to root Ka, that is this denominator root Ka multiplied by root of Kw into root of Kw, that's about for this Kw, divided by root of Kw, and that is for inside root Kw here, multiplied by root C, multiplied by root C. Therefore, cancelling one of the Kw, children, when we cancel one of the Kw, we have the entire term is, all the terms consist of root, we have H plus concentration will be equal to the whole root of Ka multiplied by Kw by C. Now you take logarithm, children. When we take logarithm, log of H plus will be equal to your, for want of space, I'll just rub off this information, children, because we have used almost all the data from the board. Now we will try to derive the final expression for your pH. Now therefore, log of KH plus will be equal to logarithm of your Ka multiplied by Kw divided by C, the whole power of, that is equal to half logarithm of Ka multiplied by Kw by C, and that is your log of H plus. Children, we know that log of A into B will be equal to log A plus log B, and log of A by B will be equal to log A minus log B, and therefore we have half into logarithm of Ka plus logarithm of Kw minus logarithm of C, because these two are in the product, and therefore we have summed up the logarithm, and the third one C is in the denominator, and therefore we have taken a minus sign there. Now we need pH, throughout multiplied by minus sign. Then we have what is known as minus log of H plus will be equal to, I multiply the minus sign inside, children, I have got half outside, half into minus log of Ka minus log of Kw plus log C plus log C. Now we know, children, what is minus log of H plus? It is called pH. pH is equal to half into minus log of Ka is called as pKa minus log of Kw is called as pKw plus log C. That's about the final expression of the pH of your hydrolysis of salt of weak acid and a corresponding strong base. Children, instead of pKw, pKw will be equal to minus log of Kw. What is Kw, children? Kw is 10 power minus 14, and therefore minus 14 will come here, minus and minus will become plus 14 log 10. Log 10 to the base 10 is 1, and therefore pKw will be equal to directly 14. So in standard textbook they would have given half of pKa plus 14 plus log C, or you can divide this 14 there, they would have given 7 plus half pKa plus half log C, or 7 plus half into the total your bracket log of Ka plus log pKa, the minus log of Ka or pKa plus log C. So the final expression can be written as, the final expression in terms of your Kw value can be written as, children, now we can write as given by your pH is equal to, pH will be equal to half of, pH is equal to half into, what is pKa? Simply we take pKa, pKw is 14 plus log C. Therefore, when you divide by 2, we have pH is equal to 7 plus half into pKa plus log C, and that is the final expression. Maybe you may have see, you will see in your standard textbook. Children, that's about the pH of the hydrolysis of salt of weak acid and a corresponding strong base. We have similar equations for strong acid versus weak base and a corresponding weak acid versus weak base, which we will see in our further session. That's all, children. Thank you for the day. Bye bye.